right, so far this year in trig, we have been looking at sets of data, and we've been fitting linear regression models to it. And we've been looking and saying, does the data look like a line? Does it form somewhat of a line? And a lot of times data is in a different shape than a line. Sometimes it fits a different function model, and one of those function models is one of the ones we're going to look at today, and that's the exponential function model. So an exponential function is of the form f at x equals a times b to the x. And in that model, a is always my starting amount. B is what we call the growth factor. Now, when we say that there's a growth factor, it's actually growing and getting larger if B is greater than 1. That's called growth. And if B is less than 1 or greater than 0, it's always going to be positive, then we say that it's decay. Now that could be confusing. Some people could say, well, wait a second. If it's decaying, why do we call it its growth factor? It's just the generic term for it. The growth factor tells us, is it getting larger, which is usually what we think of as growth, or is it actually getting smaller? And then the x is typically, in most of the scenarios that we're going to look at, time in years. Now, I'd like to go to the calculator to just make sure we really understand this idea of an exponential model and what the a and the b values are actually going to look like. So on my calculator, if I say that my starting amount is, let's say, 12, start with 12. And then I'm going to multiply by, let's make my growth factor 1.7. And that is a growth factor where that means it should grow because 1.7 is greater than 1. And then I'm going to raise that to the first power, which means I'm just multiplying it by 1.7 one time. And I get 20.4. It grew. I took 12 and I multiplied it by 1.7. Well, if I take 12 and I multiply it by 1.7 again, so in other words, I multiplied by 1.7 2 times. So it means I took 12 and I multiplied it by 1.7, and then I took the 20.4 and I multiplied it by 1.7. It's getting even larger. Another way I could do is just keep taking my previous answer and multiplying it by 1.7. It's getting bigger. Let's do it again. Let's multiply. So now, rather than multiplying by 1.7 squared and 1.7 cubed, I'm just taking the previous answer and I just keep multiplying by 1.7. That's essentially what we're doing when we have an exponential model. We're taking the previous answer and we just keep multiplying it, so it keeps getting bigger. Now, I don't know if you know this, but on your calculator, if you do something twice in a row, your calculator picks up on it as a pattern that you want to keep multiplying by 1.7, so I don't have to keep typing in times 1.7. I could just start typing in enter. It gets bigger and bigger and bigger and bigger, and look what's happening. It's just growing exponentially, getting really, really large. Now, if I did the same type of thing on clear, if I started with 12, and rather than multiplying by 1.7, I picked a number smaller than 1, like just plain old 0.7, and I just multiplied it one time. I could say to the first power if I wanted to, or just multiply it by 0.7 one time. I get 8.4, okay? Well, what if I had said take the 12, now notice it got smaller, went from 12 to 8.4, 12, and I multiply by the 0.7, to the second power. It's getting even smaller. Now, rather than using exponents, I'm just going to keep saying times 0.7. But you guys might be wondering, why is she spending all this time doing this? This is ridiculous. This is so easy. I know this. Because this is something people make mistakes on all the time in this section. They don't get that when a number like 0.7 is the growth factor, because it's less than 1, it's getting smaller. People think if it's positive, it gets bigger. If it's negative, it gets smaller. That's not true. It just has to be less than 1 to get smaller. Because if you notice, I'm just going to keep hitting enter here, it's getting smaller and smaller and smaller and smaller. Because the thing I'm multiplying by is less than 1. I know that was a long explanation, but I have learned from previous experiences that it's something really important for me to show you. All right, so let's start looking at the different type of exponential functions, because this is the generic form for an exponential function, but most exponential functions deal with real-world problems, and so we need to kind of look at different models for them. So exponential growth, the way that model sometimes looks is A equals P times 1 plus R to the T. Now, believe it or not, this is actually the exact same formula as this right here. Instead of saying f at x, we're saying A, which stands for total amount. So this is when we're just looking at numbers and we're writing it in function notation. This is in a real life problem. The total amount is going to be that f of x. P, which is the same as your A, is your principal amount. Now it's spelled like principal, like Mr. Collins is our principal. However, principal amount means starting amount. In a bank, when you go and you take an amount of money and you put it into a savings account, that's called the principal. What did you start with in your account? When you're studying populations, whatever year you begin and you say the population at that starting year was this, that's the principal amount. The 1 plus R is the B that's greater than 1. It's 1 plus R because we want it to be greater than 1. And that R is the rate. And you have to convert it to a decimal because you don't want to leave it as a percentage. And then T is going to be your time in years, just like your X. All right, so let's look at example 1. 5,500 is invested in an account with a 4.5% annual yield. This is the amount that is invested. That's going to be my principal. The 4.5% annual yield is my rate, but that's written as a percent, and I need my rate written as a decimal. So when you go from percent to decimal, you move the decimal place 2 places to the left because percent means per 100. So that's going to become 0.045. What is the yearly growth factor? Well, this right here, remember this is my growth factor. B is my growth factor, which means 1 plus R is my growth factor. So 1 plus 0.045, or we could just simply say 1.045 is my growth factor. All right, what is the balance after 18 years? All right, so what's my amount going to be? My principal is 5,500. My 1 plus R I know is 1.045. And 18 years, that's going to be my T to the 18th power. So I'm going to go to my calculator and I'm going to type this in. I like to do this with you to make sure that many times I have found that people type things into the calculator wrong, which is why I show you what it should look like on your calculator. So make sure you're doing this. Some people are like, oh, if I just watch you, that's good enough. If you wanted to be a professional football player, could you just watch football for like 10 years? Just watch every game you could. And then you could just go try out and be like, yeah, I'm ready to be a professional player. No. Oh, I did not mean to do that. I was talking and kind of got delete. Okay, let's try that again. To the 18th power. And I get, that's fine now. I'm going to round it to the nearest penny because this is money. All right, so now we've written down our answer for our exponential growth model. Let's look at exponential decay. It's pretty much the same formula as exponential growth, where A is the amount, we have P as the principal, but here is where the change is. Because the growth factor is no longer growth, but it's decay, the growth factor has to be between 0 and 1, so we say 1 minus the rate, as opposed to 1 plus the rate, right, to the t. So we're still going to have A is the amount, P is the principal, R is the rate as a decimal, and T is time in years. So let's look at our example. A new car is currently valued at $25,000 and depreciates. That means it's decreasing in value. That's why it's 1 minus R, 2% each year over the next decade. What will be the value of the car in 8 years? So I'm going to reread the problem and look for where I'm going to be substituting these numbers. It's currently valued at $25,000. That's going to be my P. 2%, that's my rate. And I need to convert that to a decimal, and 8 years, that's my time. All right, so A equals my principal, which is 25,000, times 1 minus 0.02 to the 8th power. I'm going to go ahead and put that into my calculator. All right, and when I typed that into my calculator, I got my answer of $21,269, and I would say 8 cents. Want to just clarify, we're going to round the same way we always would round. 4 and below, let it go. 5 and above, give it a shove. So if you're trying to figure out if it's 7 cents or does it bump up to 8, you look to the right. That 5 is going to bump that 7 to an 8. And so I have $21,269.08 is going to be the value of my car after 8 years. So let's look at how do the values of A and B affect the graph of the function. All right, so we're going to look at an example of this, but A is the starting amount, and whenever you have something as a starting amount, just like in a linear function, the starting amount is where it crosses the y-axis. It's the same thing in an exponential function. So A, which is your starting amount, is going to be your y-intercept. It's going to be where it crosses the y-axis. And your b value is going to be increasing, so the curve is going to be going up if b is greater than 1. And if it's decreasing, the graph is decreasing, that's only if b is between 0 and 1. Notice it's never going to be negative. We don't have a growth factor is either a decimal that's really close to 0 or somewhere between 0 and 1, or it's greater than 1. And let's look at an example of this on the calculator. All right, so I'm going to use that equation that we looked at on the calculator earlier, 12 times 1.7 to the x, and I put that into y equals, and let's look at the graph. If you look at the graph, it is going to cross the y-axis at 12. If we were able to count these, that's going to 12. And then if you look from left to right, it is always increasing. Now let's go and change our equation just a little bit. Let's go ahead and make that 12 times 0.7 to the x. And it should still cross at 12 because it's still the starting amount, but this time it should be decreasing as opposed to increasing. And you see that difference. Crosses at the same place at the 12, but from left to right it's decreasing.